Hello, I'm here to talk to you today about waves. Now, waves is a unit that has a lot of vocabulary to it, so you're going to want to pause the video at times to make sure you have time to write everything down. You're going to have to memorize some of those vocabulary terms so you know what's going on too. I want to just start by defining what a wave is. A wave is a transfer of energy. So you'll see matter moving around in a wave oftentimes, or particles moving around. But ultimately, what is moving down the length of the wave is energy. And we'll look at that a little bit in class. Now, we say waves move through a material. The material is also known as the medium. That's the material through which a wave travels. Now, not all waves need a medium to travel through. Some things like light can travel through space, which is a vacuum, and has no material to it. But other kinds of waves, like sound, do need a medium. So sound can travel through the air. The air provides a medium through which that energy is transferred. Sound can also travel through solids, for example, or liquids if you get into a swimming pool. So there's different kinds of media and different kinds of waves that travel through different media. This is a wave that I have drawn right here, and you'll notice that I've identified the peak to the wave, and then there's also another peak. There's what we call a trough to the wave as well. So some terms that we use to define the shape of a wave include wavelength. Wavelength is a length, right? And so it's often measured in meters. It is just the length of the wave. Now, the length of the wave can be considered from peak to peak. So for example, from here all the way over to there, that would be the wavelength. And we often see the wavelength denominated by this term, this Greek letter called lambda, like that. So the length of a wave is also known as lambda. You can also say, for example, it is from like trough to trough. So if we had a trough here going all the way out to the next trough, that would be one wavelength. One wavelength. Or like from here all the way, not to where it crosses here, but there, that would be considered one wavelength as well. So all three of those represent one wavelength, and if you were to measure them, assuming that this is a symmetrical wave, then that length would be the same for all. Amplitude is the height of the wave from the middle. Now, you need to be careful because amplitude can be measured in different units. Sometimes it's measured in meters. In a wave like this, it could be measured in meters. But sometimes it'll be measured in different things. Like sound waves, the amplitude is related to the loudness. So it's not going to be a unit of meters. And so if I were to draw the amplitude of this wave, remember it is measured from the middle. So there's the peak, there's the trough, this is the middle. The amplitude would be this distance there. I'm just going to write A for amplitude. Now that distance there is the same as this distance here from the trough to the middle. So the amplitude in both cases would be the same distance. But don't get confused. If you go from the bottom to the top, that would represent a distance of two amplitudes here. You will see the term frequency. Frequency is measured in hertz, and frequency goes by the letter F. Sometimes it's a kind of fancy F, like a curl. And that is the number of waves per second. So a 600 hertz wave would have 600 waves per second. Similarly, the period is the number of seconds per wave. You'll notice that they are exactly flip-flop. They are the opposite. The number of seconds per wave, the period often goes by the letter T, and it is measured in seconds. It is a unit of time. You could measure it with other time units if you want, but most typically we'll measure it in seconds. And what we're going to find later on is that the frequency and the period are inverse of each other. So the frequency is 1 over the period, 1 over the period, and the period, T, is equal to 1 over the frequency. If you look at the units of hertz, a hertz, if period's in seconds, frequency, which is 1 over time, would be measured in 1 over seconds. So a hertz, technically, is just 1 over a second. Now, you'll notice that it's number of waves per second. Number of waves doesn't have a unit to it. The only thing that has a unit is seconds. So Hertz itself is just designated as a number of cycles of something. We don't necessarily know what it is, but in this case, the number of waves per second. So this is a specific kind of wave. I want to talk a little bit about different kinds of waves, because there's lots of ways we can break these waves down into different parts. I'm about to erase this right now, so pause it if you need to write anything down. I'm going to start by just going away with this. Now let's talk about different kinds of waves. There's two main kinds of waves we're going to see. The wave that we have here, right there, that is known as a transverse wave. And a transverse wave shows the sinusoidal form. And if you could look at the particles within a wave, like ocean waves often look like sinusoidal waves. They're not exactly, but light is a sinusoidal wave, for example. Light is a transverse wave. In a transverse wave, what we find is that particles in it, so maybe this is a drop of water in the wave. The drop of water, as the waves pass by, would go up and down, and up and down, and up and down, and up and down. So those particles move up and down, even though the wave might be moving to the right. So in a transverse wave, the particles move, I'm going to say perpendicular to the wave itself. Meaning if the wave is going to the right or the left, the particles vibrate up and down. So their vibrations in the opposite direction. Now, this is different than what I'm going to draw over here, and that would be a longitudinal wave. And then a longitudinal wave is also known as a compression wave. So a compression wave looks different significantly than this, but it has many of the same things. It has a wavelength, an amplitude, a frequency, and a period, for example. So a longitudinal wave, for example, sound is a longitudinal wave, whereas, example, light is a transverse wave. Might look a little bit like this. These might be air particles, for example. And you get what's called compressions, where all the particles are close together, and then they space out again. And then you get another compression. And then they space out again. And then you get another compression. Etc., etc. So these compressions are sort of like the peaks in this wave. And in between the compression, you have what's known as a rarefaction. And a rarefaction is where it is spaced out. So for compression, whereas it's compressed tightly together, rarefaction is where it's spaced out. And you could measure the wavelength of this wave, and you would see that the wavelength, which would be, for example, like peak to peak there, or peak to peak here, that is your wavelength. And you could measure the wavelength just like you did with this wave as a distance, right? Other things like amplitude are much harder to draw or represent in a drawing like this, so I'm not going to do that. Its amplitude in a sound wave, for example, is not going to be measured as a size. It's going to be measured in some other form, an intensity like a loudness, for example, as amplitude is related to loudness. You could also measure a period, for example, which would be if you're standing over here and this wave is moving toward you. Let's say your person is here. That person could observe the waves coming towards them and see how many waves pass per second, and that would be the frequency. So that frequency in sound waves is related to pitch, like ah is a different frequency than ah or ah. Period is the time per wave, so you could measure how long it takes one wave to pass you, so that would be like from compression to compression. How much time passes, that would be your period. So that is the difference, two main different kinds of waves. A transverse wave like this, and if you think about it, transverse T, you have the particles moving in one direction, whereas the wave is moving in another. They make that kind of T-shaped, as opposed to a longitudinal wave, where if you watch any individual particle in the wave, that particle goes left and right and left and right and left and right. So in a longitudinal wave, the particles move in the same direction, as the wave. So two different kinds of waves. Now, as I break these waves down, we can further categorize them. So there are a couple different kinds of waves. One, for example, would be a pulse. So a pulse is just equal to a single wave. So if instead of sending a whole bunch of things like this, you just sent one really quick pulse of noise, that would be like a pulse. This is different than a repeating wave, which would be called a periodic wave. And that's a repeating wave. Now, a repeating wave could be like if you're standing over here, maybe you're at the shore of an ocean and you watch wave after wave after wave coming, and they might all have the same wavelength, for example. That would be called a periodic wave. So a periodic wave continues coming at you for a long period of time, different than a pulse, which is just a single quick burst. There's another kind of wave that you see too, that's called a standing wave. And I'm going to define that more in the future, but a standing wave is really the result of what we would call interference, or two waves coming together. Interference between two waves. So if two waves pass through the same location at the same time, we get this result called interference. And the standing wave looks more like something like this. I'm going to just draw this here as I erase some stuff. I'm about to erase this as well. So if you need to go back and look at any of it, you're more than welcome to do so. Just rewind the video. A standing wave looks a little bit like this. And in a standing wave, you have what are called nodes. Which is the null point, aka the null point, meaning the 0 point. And you have what we would call the antinodes here, where the wave oscillates up and down and up and down and up and down. So the wave here would not move much at all, but here it goes up and down and up and down. And again, this is caused by multiple waves that interact with each other as they pass through the same space. One thing that you do need to know about a standing wave is that the wavelength is defined as the distance between two peaks. But when the wave is at a peak here, or a trough here, it would be a peak there and a trough there. So technically, a wavelength is going to look like that, one wavelength. Because if this is oscillating back and forth, and you'll see this more in class, when it's high here, it's low here. When it's low here, it's high there. So at any given time, one full wavelength is going to look like that. And the amplitude, just as we mentioned before, is going to be there from the middle to the top. Let's see. Other things we can talk about with waves. I'm about to end this. But I did want to mention a couple different things, is that we will talk about velocity of a wave, or the speed of a wave, either way. And we're going to talk about energy. And we have two ways typically to get velocity or speed, which will be a separate video. And energy can be related to multiple things, like more energetic waves can be more energetic because they have a higher amplitude, or they can be more energetic because they have a higher frequency. So different kinds of waves, it might depend on different things. It may depend on amplitude, such as for sound waves, or it could depend on frequency, such as for light waves. That's a lot to digest, I know, so feel free to rewind and rewatch. Make sure you get the terms written down and ask questions if you have any. I think that's it for this video. Thank you very much for watching.